name is Hobbs. I'm a system software developer in LC, and I work with a lot of our flux-core developers. And I'm going to talk about different ways that you can extend or add plugins to Flux. So tapping into job state, validating different jobs, and then using like elevated privilege prologues and epilogues to customize things for a center-wide deployment. So all of the Flux core interfaces, so all of the things that you would see in like the Flux core GitHub repository, are designed to be extensible. I'm going to talk a little bit first about like some of the low-level architecture of like the low-ish level architecture of Flux, and then building up from that low level, talk about broker modules and Jobtap plugins, which are kind of a plugin to a broker module. Validator and frobnicator plugins. I think we made up the word frobnicator, but we didn't make up the word validator. And then how we extend the Flux command line. So like Ryan talked through some of the differences in the Flux command line and the Slurm command line. A lot of centers had their own Slurm plugins to extend the command line, and we can do that too. But one thing that I wanted to point out first is that all of the projects that we talk about being in the Flux framework, so like Flux Sched, Flux Accounting, they rely on these core set of plugin interfaces to implement their own functionality and kind of coordinate between these different plugin interfaces to implement a scheduler, to implement, I think Jay will talk about later, like job modeling. The question we often get, and I kind of said this, is like, how do I customize it? So if my center has this weird type of hardware like an AMD APU that can be split into 4, 8, or 16 GPUs, how do I customize Flux to be able to handle that? How do I customize Flux? Chris has added a lot of custom plugins to be able to track specific types of users' jobs. How do I impose limits on users' jobs? If I want to add shortcuts for commonly used submission commands, how do I do that? And one thing that's really useful that I found really useful as a developer on Flux is that almost all of our customization interfaces with varying difficulty can be done in Python. So it can be either prototyped or fully written in Python. But a lot of the core functionality its kind of native language is like loading a DSO. So at the lowest level of Flux core implements a distributed overlay network. So each node in a 4-node cluster, like I have in my apartment to play with, has a broker. And so the broker is just a process that's running on the node. And each broker has a connection to a parent. So it can communicate with its parent broker and send and receive messages. The tree structure can be configured by users and admins to be different things, but we typically use flat trees even on our very, very, very large systems. There's a parent and then a fan out of about 10,000 brokers. And each broker loads modules. So these are typically like DSOs. They're written in C, and they define a set of functions that happen when you receive a message and set a callback to fulfill some amount of work whenever the module receives a message. And modules will send and respond to messages over TCP/IP via 0MQ sockets. So this is all encrypted, and we use 0MQ's messaging for that. So if you log into a login node on an example cluster like I did earlier today, and you just look at what modules are loaded, you'll see a bunch of different broker modules that are just sitting loaded in your local broker. But if you look at a set of broker modules on an example like rank 0, like at the top of this broker tree, you'll see some special broker modules. Like the scheduler is a kind of special broker module that's only running on rank 0 of a system instance. And I'll talk a little bit later about the topmost kind of special one, which is the job manager. So how are modules driven by messages and callbacks? So the kind of in real life example of this is I'm a user on a login node and I want to run a job. So what I do is I flux run and I use all the commands that Ryan just talked about. And what this is really doing is it's sending a message. So the job ingest module on the login node sees that the user, this Python command that we have has constructed a message and wants to send this message. So the module on that node picks up that message and recognizes that I'm on a login node, I can't do compute here, I need to route this message appropriately. So it routes it up the tree to the job manager on the management node, which is involved in the state transitions of the job. And then the management node recognizes, hey, I'm a management node, I can't run this work here, I need to dispatch this work to the compute nodes to be able to fulfill this user's request of getting their work done. And that's kind of a simple example of how messages and callbacks are the fundamental layer of Flux to enable all of the like really important, job states and features that we have for our users. All of our jobs in Flux go through this state transition diagram. So this is written up on our website in a request for comments. And the job manager, which is one of the broker modules, is involved in moving jobs through all of these states. But in between all of these states, the job manager allows you to register callbacks. So you can say in between any of these bubbles or arrows, I want the job manager to perform some task in between the states of every one of my jobs or a subset of my jobs. And these job manager plugins are typically DSOs, so they're C files that you compile and you load a DSO. But we've tested with Python CFFI generating a DSO, and it actually does work. So if you wanted to prototype a Jobtap plugin in Python, you could do that. Both jobs at the system instance level and jobs within your instance. So if I flux alloc and I get an instance and I now have my own job manager that I own and my own scheduler, all of my jobs are continuing to go through this state diagram. We don't have a concept of job steps, we just have jobs. And what that means is that if I have, my allocation and my instance that I own, I can load my own Jobtap plugins, I can load my own broker modules, I can manage these plugins in whatever way I want to within my subinstance. A question came up earlier about prologues and epilogues. So the actions that need elevated privilege to work before and after a user's job starts happen on each individual node in their allocation before and after the run state. So when a user starts a subinstance, that subinstance will be a job that's in this run state. They'll then have their own set of, they'll have their own job manager, they'll have their own broker tree. We don't allow users, we don't have any way to allow users to then like have another prologue themselves, because that would kind of bypass their privilege. So this is something that kind of trips up users, but all the other plugin interfaces that we've named, like Jobtap plugins and broker modules, can be loaded by the user in their subinstance. So here's an example use case for plugins that we support on LCAP. This is some work that Jim Garlick did to support the Cray VNIs. So the Cray VNIs are kind of like a network namespacing. They're kind of like a network namespacing tool for LCAP, the Slingshot network. So they need we have a set number of them, and they're assigned an integer, and the job gets assigned an integer, and then it's tagged with a VNI. And so in the sked state, you'll see there's a Jobtap plugin that keeps a record of these integers that is handed out. So there's 0 to 64K integers. It keeps a record of the ones that is handed out. When a user hits that state, they get assigned an integer. It gets added as an annotation on the message that is their job. And then when they hit the run state, the prologue takes this integer from the metadata about the job, starts up their network namespace, and then tears it down at the end, and the Jobtap plugin, after their job is completed, releases that integer back into the pool that it can assign to other jobs. So this is one example of how both a Jobtap plugin and a prologue epilogue can interplay with each other to enable some kind of functionality. This last box on this slide, you'll notice we're kind of back where we started a couple previous slides ago, but before that message that is the user's job ever gets transmitted, we also have the ability to kind of add plugins to the command line. So the user never really sees their message unless they're really interested. They just type things on the command line like flux run and with their flags, and what that does is it actually starts a Python script as them and constructs a JSON object called a job spec. After that job spec is constructed, another broker module, the job ingest module, validates it, so it looks and makes sure that it's valid JSON, and we have a set of. The validator allows you to add plugins to it. So you can define a Python file that says, hey, I want every single one of my jobs, in order to be considered a valid job, to have these attributes. You could load that in the validator, and the validator would check that all of your jobs meet those criteria. We also have frobnicator plugins, which modify existing job specs. So if you wanted to say, hey, if a job doesn't set a time limit, and we've implemented this by default already, but the way that we implemented this is we said, hey, if a job doesn't have a time limit, we want the default time limit to be 8 hours, and that's enforced by a frobnicator plugin. Command line interface plugins wrap up a couple of these interfaces together. So I've already said that Flux Run and other command line submission tools are just constructing JSON messages that are being transmitted over the overlay network. And the Python tool that's actually doing that construction is you. So it starts under your user. So anyone, whether they own the system instance or not, can add an arbitrary long option to this Python script that'll allow you to like wrap multiple options into kind of a shortcut. Only the instance owner can register a CLI plugin that also includes a validate callback, but that's because the validator is running as the Flux user and not as you. So we used this to make it a lot simpler to support the AMD GPU modes where they can be split into multiple GPU nodes, because for a while we made users write things out. And if you thought they were cranky because we use P and not Q, they're really cranky when they have to write out this many things to get the functionality that they want. So by being able to wrap a lot of different flags into just one, we can better, we can make the users happy, which we try to do when we can. So this is kind of an example of how a CLI plugin would interplay with a prologue. So if at submission time the user adds a flag to their job, then that gets added as an annotation on the message that moves through the state diagram, and when it gets to the run state, the prologue can pull down the job spec and see that they requested a certain GPU mode. And then they can, the prologue has to turn LDMS off. That's kind of the elevated privilege piece of it. Reconfigure the GPU, and then give the user the GPU that they requested, and then after the user is done, put it back into some kind of default setting. So with that, that is kind of a quick overview of some of the low-ish interfaces in Flux and the ways that you can customize them, and I'm happy to take any questions about that.
Hey, thank you for that introduction to the plugins. So I don't remember exactly where I was doing the documentation, but I think Flux has some facility to handle like node failures or redundancies, maybe. And I was just like looking at all the state diagrams. I was just trying to think of like how much one has to think about when trying to use these plugins, about what is failure resistant or prone, or like, how you would work within that kind of recovery.
So if the management node fails, it's bad, but that's pretty much universally true. When I think about this, I went back to this because I think that looking at the cluster through the lens of kind of the overlay network helps. So we have modes for fault-tolerant recovery on the children of the overlay network. So if one of the compute nodes goes down, the broker will lose its connection to its parent, but the entire tree can tolerate this. When the node comes back up, it can reconnect to the management node. But the kind of critical point of failure is if the management node loses its connection to its children. We don't currently have a way to reconnect the parent management node to all of its children. This is why we're running flat trees, because if you imagine like if we had a binomial tree where every parent only had 2 children, if any parent in that tree goes down, it loses all the connections to its children. That's actually one of the things. Tom had a slide earlier about like upcoming work, making the broker trees more resilient for restarting or rolling updates. That's kind of the first step, is making the broker tree more resilient to parent failures.
Okay, so then for the non-management node failure, so would you typically, so how much do you interact with Flux in making your application resilient to those like compute node failures? Or
I'm gonna phone a friend on this one, because I think.
So let's say you have a compute node go down, right? So Flux is aware of this, it manages some state, and with respect to that. So how much of like your application needs to know about this or adapt to that failure?
As a user application? Or
Yeah, so, well, like, I think with Slurm, you could link to libslurm and get, information about what Slurm knows, right? And so I'm trying to understand what the equivalent in Flux is.
I think.
You can link to libflux, you can send messages, you can query the state of things. We have users that, like by default, if a compute node in your application fails, frequently that means that your API job, whatever you have, fails and then dies. We have users who don't want that, who want to be able to allocate a couple extra nodes, be able to restart within that allocation. We do support sometimes it takes a little extra configuration on the sub-instance you run in an allocation that you want to be reliable. We have some documentation on that I'd be happy to point you to.
Okay.
It depends a lot on how you want to handle your resilience, because for a lot of users, it's fail and retry at next checkpoint is what they want. So that's kind of our first support thing. But we have other options for more interesting use cases than that.
Okay.
So I'll just add to that we have one of our broker modules is a resource module that keeps a track of the state of the node. And I believe that the resource module contains a journal that you can subscribe to and get updates about the state of the state of nodes within your allocation. That might be of use here. The other thing I wanted to say is that as Tom brought up, we have some users that want specific resiliency features. At the system instance level, a flat tree is very common, but it doesn't have to be the case for your allocation. So you can set up your broker tree and your allocation however. You can configure the broker tree and your allocation however you want. And we have some specific configurations that I think we made for the AI users that have more, fewer critical nodes that helps with resiliency.
Okay. Thank you.
Am I out of time? Oh, I have 5 more minutes. Okay.
Okay, so building on that question a little bit, are there plans to do something like a primary-secondary functionality where instead of having child nodes and parent nodes, you could have 2 parents that are 0 and 0 apostrophe or something, 2 back-end level controller nodes where if either one of them goes down, the other one could hop in place for the others, so that you could have, inside of your allocation, I want to dedicate 3 nodes inside of my allocation to be controllers and be managing everything just in case one of them dies.
So we have a broker configuration called mincrit that's supposed to minimize the number of critical nodes in the tree, and I'm not sure that it does. I'm not sure it does exactly what you're describing. I am not. If you're talking about the plan for resiliency at the system instance level for restart, I'm not exactly sure we've made it that far in the planning of how we're going to handle that.
Yeah, I just think of, I guess this conference in particular, but a lot of folks, especially in the cloudy space, if you were working on spot instances and you couldn't guarantee that one of them wasn't going to be revoked from you at some point, it would be really cool if you could say, even if this is a little bit less efficient, I want to do something more a little bit like Kafka, where I could blow out the number of system brokers so that if any one of them is scrapped or something bad happens to them, I have resiliency and all of my login nodes or compute nodes would just shift who they're talking to over time.
Yeah, I don't know, in today's Flux, I don't know how that would work with the critical set of broker modules that we have running on rank 0, the scheduler and the job. If you had multiple of those,
Right.
I don't
Right, you would have to do some
Yeah, you'd
raft consensus algorithm or something to have one of them be primary